Good evening to all. Today I am going to present a lecture on real analysis, program BSc, subject mathematics, semester 5th semester, chapter Riemann Integration, and name of the presenter Dr. Sridhar. So let us start. So today we are going to learn about algebra of integrable functions. So here the first law is integrability of product. So it says that if f and g are two functions, both bounded and integrable in the interval ab, then the product f into g is also bounded and integrable in the interval ab. Okay, so this is the statement. Now we prove this. Okay, so now let us take two functions, say f and g, and let these two are bounded. Okay, these two are bounded and integrable, right? So now by the definition of boundedness, if f and g are bounded, then there exists a number k such that for all x belongs to the interval ab, absolute value of f of x is always less than or equal to k. And similarly g is also bounded. We have taken g is also bounded, so therefore absolute value of g of x is also less than or equal to k. Okay, so how we have taken this one? So because f and g are bounded, and therefore by the definition of boundedness we took this equation. Okay, so then this means now taking the product, multiply those two, f and g. So then what happened? F into g, f of x into g of x, it gives again less than or equal to k into k, because we are multiplying the two functions, so k into k square. So that means absolute value of f of x into g of x is also less than or equal to k square for all x belongs to ab. This means, now see here again, this means absolute value of f of x into g of x is less than or equal to k square. So means k square is again a constant, k into k is again a constant because k is constant. So therefore what we are getting, absolute value of f of x into g of x is less than or equal to a constant. So this means f into g is bounded. F into g is bounded. Okay, so now we prove fg is integrable. F into g is also integrable. So for that what we do, we consider a partition P. Okay, so which is where the set contains a equal to x0, x1, x2 and so on, xr minus 1, then xr and dash 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 xn, which is equal to b. Okay, let this P be any partition of a closed interval AB. So partition means a part of a interval, okay, let it is a partition of AB. So then, so when we consider a set means, then there may exist lower and upper bound, right? So now here what we do, let capital MR dash then small mr dash be the upper and lower bounds of the function f. Okay, and similarly capital MR double dash, small mr double dash are upper and lower bounds of the function g. Okay, then capital MR and small mr be the bounds of the product f into g. Okay, is it clear? So then respectively in the interval xr minus 1 to xr, then for all we have, for all alpha 1 alpha 2 belongs to this interval, then we have absolute value of f of alpha 2 into g of alpha 2 minus f of alpha 1 into g of alpha 1. Let us take this one. Okay, for all for any two elements, say alpha 1 and alpha 2, which belongs to this interval, let us consider the equation this one, f of alpha 2 into g of alpha 2 minus f of alpha 1 into g of alpha 1. Okay, so now in this case we add and subtract f of alpha 1 and g of alpha 2. Right, here what we do in this case, we add f of alpha 1 into g of alpha 2, and immediately we also subtract f of alpha 1 and g of alpha 2, so that the value does not change. Okay, so then after adding and subtracting, now see here f of alpha 2, okay, and g of alpha 2, its term is here, right? Then similarly f of alpha 1 and g of alpha 1. So now here this is f of alpha 1, then g of alpha 1 minus, it is the two terms are here. Only the what we are getting, f of a2 and f of alpha 1, then f of alpha 1 g of alpha 2, we are getting this term as new. So that means we have added and subtracted those terms, right? So then in this grouping, and then we take g of alpha 2 common, and in the first term we get f of alpha 2 minus f of alpha 1. Then similarly taking in the second term f of alpha 1, then we get g of alpha 2 minus g of alpha 1. Okay, so this means absolute value of, taking the absolute value for both the terms, right? So then absolute value of f of alpha 2 into g of alpha 2 minus f of alpha 1 into g of alpha 1 is less than or equal to. Okay, now already we have learnt one theorem, that is absolute value of a minus b is always less than or equal to absolute value of a plus absolute value of b. Okay, so same formula we are using here. So now so therefore is less than or equal to absolute value of f of alpha 2, okay, f of alpha 2, then into then f of alpha 2 minus f of alpha 1. Now here see here, this is absolute value, okay, taking the absolute value for both the terms. So this becomes absolute value of f of alpha 2 g of alpha 2 minus f of alpha 1 g of alpha 1 is less than or equal to. Now here also we have taken absolute value. So absolute value of g of alpha 2 into absolute value of f of alpha 2 minus f of alpha 1 plus absolute value of f of alpha 1 into g of alpha 2, absolute value of g of alpha 2 minus g of alpha 1. And also we know another one more theorem, that is absolute value of AB. Absolute value of AB is equal to absolute value of A into absolute value of B. Okay, so the same we are using here. So now see, this is the product. Okay, now this is the product. When you take the absolute value, this becomes A and this becomes B. So absolute value of AB is always less than or equal to absolute value of A into absolute value of B. Similarly here, absolute value of f of alpha 1 into absolute value of g of alpha 2 minus g of alpha 1. Okay, so now this means less than or equal to. Now this absolute value of g of alpha 2, because g is bounded, so therefore its absolute value is less than or equal to k. Similarly here f of alpha 2 minus f of alpha 1 becomes, now see this capital MR dash is the upper bound of the function f, and small mr dash is also the lower bound of the small f. So therefore f of alpha 2 becomes capital MR dash minus f of alpha 1 becomes small mr dash, because they are upper and lower bounds of the function f. Then plus, similarly the function f is also bounded, so therefore its absolute value is equal to k. So I have replaced this by k into, now here g of alpha 2 minus g of alpha 1. Now this mr double dash is the upper bound of the function g, as already we have considered this one. Then similarly small mr double dash is the lower bound of the function g. So therefore this g of alpha 2, we have replaced this by capital MR double dash minus this by small mr double dash. Okay, so then this is equal to less than or equal to. Now less than or equal to, what happened then, mr minus mr is, now see here this left hand side, this is the capital MR minus small mr dash is equal to, because this f and g is both mr and small mr and capital mr are the upper and lower bounds of the function. Okay, so therefore this is less than or equal to k into, this is mr dash minus mr dash plus k into capital mr double dash minus small mr double dash. Okay, so now let epsilon be any positive number. Okay, let epsilon be any positive number. Then since f and g are integrable, because f and g are integrable, then there exists a delta greater than 0 such that for every partition of norm less than or equal to delta, the corresponding oscillation sum for f and g are both less than or equal to absolute value, epsilon divided by 2k. That is, as we know that by the definition of the integrable functions, because f and g are integrable, when f and g are integrable, then clearly what happened by the definition of the integrability, the oscillatory sum, that is the oscillatory sum means oscillatory sum of f and g are both is less than or equal to epsilon divided by 2k by the definition of the integrability. So okay, so therefore now this is what, this is less than or equal to epsilon by 2k, and similarly this is also less than or equal to epsilon by 2k, because these are both f and g. So f is also integrable here, g is also integrable, so therefore it satisfies this law. So what we do, we replace this term by epsilon by 2k, and similarly we replace this term by epsilon by 2k. Okay, so after replacing, what we get, so this is summation of mr minus mr. So where mr and capital mr and small mr are the upper and lower bounds for the function f into g, so therefore this is equal to less than k into, this is replaced by epsilon by 2k plus this k into, this is replaced by epsilon by 2k. So now k get cancelled, so epsilon by 2 plus epsilon by 2 gives epsilon. So which means that fg is integrable in AB, which means that fg is integrable in AB. So therefore fg, the product fg is also bounded and integrable. So this how we prove this theorem. Okay, so next we have another law, that is integrability of quotient. So it says that if f and g are two functions both bounded and integrable in the closed interval AB, then there exists a number t greater than 0 such that absolute value of g of x is greater than or equal to t for all x belongs to the closed interval AB. Okay, so then f by g is also bounded and integrable in AB. Okay, so this is the integrability of quotient. That means if f and g are two functions bounded and integrable, then f by g is also bounded and integrable. Okay, so I left this theorem as an exercise, so try to prove this theorem as we proved in the last, that is a product of two functions. Okay, so therefore in the same way try to prove this one. Next, another we have integrability of modulus of a bounded integrable functions. So here it says that if f is bounded and integrable in the closed interval AB, then absolute value of f is also bounded and integrable in the closed interval AB, and absolute value of integration from a to b f of x dx is less than or equal to integration of a to b absolute value of f of x dx. Okay, so this is what the law says, that is integrability of modulus of a bounded integrable functions. So this is also same as we proved in the last two theorems. Okay, so then next we have integrability of modulus of a okay, this we have proved now. So next, integrability of sum and difference. So it says that if f and g are two functions both bounded and integrable in the closed interval AB, then f plus r minus g are also bounded and integrable in the closed interval AB, and integration of a to b f of x plus r minus g of x dx is always equal to integration from a to b f of x dx plus plus or minus integration of a to b g of x dx. Okay, so this is integrability of both sum and difference. Okay, so that's all for today's session. In the next class we take another chapter. Okay, thank you.